Welcome, this is Algebra 2, Semester 1, Unit 2, video number 2. This is on reflections. Reflections are so cool. You know about reflections. I drew my little man up here at the top, and he's looking down into a pond and seeing his reflection. You've probably done that before, looking down into water going, whoa, look at that reflection coming back up. Same thing happens in math. Math is all about nature. It makes sense. It should always make sense. If it's not making sense, then you need to find another resource to explain it again. And keep viewing videos, keep talking to people. Math will make sense. Don't give up on yourself. I'm going to expand this out just slightly, come up just a little bit. Okay, in the last video we talked about the linear parent function. So as we plug in x, just a reminder, f of x is just the formal name for y. Okay? F of x is simply saying that it's a function of x. It's announcing the relationship. Kind of like for me, you might know me in a setting where you would call me by my first name, Tammy, and have that y. For all of you, I don't allow that, and I just think that it's improper within the classroom. So I ask you to call me by my formal name, Mrs. Kane, but I'm still the same person. So Mrs. Kane signifies that I am married. I have that relationship with that domain or demand. Okay, and so that just is another way that we can write them. Again, the linear function, if you haven't seen video number 1, you need to go watch that first. But we saw in that video that for every point on x, it came out as a point on y, and when we graphed it, it looked like this. Now, our question is, how can we get this blue reflection? Notice how the reflection looks just like me, but it goes across this horizontal line of me laying down on the ground. So in other words, I'm trying to find how I could look down and see a reflection down here. Well, that point would be reflected right there through the pond water. If this was our pond, this x-axis was our pond, this point here would look right there, and this point here would look right there. So let's look a minute at those points. Just take a couple points there. This, in our parent function, was the point 1, 1. Now in our reflection, we're going to end up with the point 1, negative 1. Interesting. And our point 2, 2 ends up being 2, negative 2. Now remember, y is completely dependent upon x. All that y becomes is the input of x and whatever we do to him. So originally in this linear parent function, we had y equals x. So she reflected him. We plugged in y, it equaled y. But now we say, well, we want her to become the opposite of him. Well, to get the opposite, see how we have the negative on her now? All we need to do is put that negative. And that becomes our reflected function. So, to graph this, we would have that reflection over the x-axis, but realize with a linear, it's going to keep going both directions. So it's kind of like this amazing pond that ends up down below us, but then up above us. It's a complete reflection. By putting that negative right there, we have taken and reflected our line across this x-axis. So it comes, this part comes down here, this part goes up there, and there's our reflection. There is our reflecting equation. Now in math we see that patterns hold true so often, and really math is the study of patterns. So we come up to our next one, absolute value. If you remember from video number 1, absolute value graphed as the V shape. Make sure that you've got a ruler, please. I have them in the cabinet. If you need to just lightly sketch it and tomorrow in class, get a ruler on it, that's fine. Or you can use your phone as a straight edge something. So, we have the absolute value in the V shape. Now a reflection of it, let's picture that. Here's our pond line here at the x-axis. This will reflect down, this will reflect down. That pond doesn't seem quite as funky to me because we're going to see it coming down in here if your mind's eye with me, looking right down on that side. So what happens again? Here at this point we have 1, 1. At this point we have negative 1, 1. And again, when we do the reflection, we don't change our x, he's independent. But we want that 1 on the y to become negative 1 down there. We want the 1 on the negative 1 to become negative 1. We say, well, how do we do that? Well, all that we're doing is we're taking our y output and we're wanting it to be negative. So we put the negative in front of the x to show, hey, we will take the absolute value of x, but then we're going to just make it negative to get that reflection across the axis. So if we were to plug points in, we would exactly get that negative, because the absolute value of 1 is 1 times the negative is negative 1. Absolute value of negative 1 is 1 times the negative is negative 1. And so on and so forth, right down through all these points. If this video is moving too fast and you want to actually plug those numbers in and see this work out, I do have a number of worksheets that you can get from me and actually use one of our graphing calculators or even just a regular calculator. Plug those in and see how it comes out. Okay? So, there we go. Now let's just stop for a minute and go back and do the domain and range. We covered that in the last video again. Let me see if I can get down here to it. Okay, domain and range. The arrow is going on and on. We try to bring in our limits from left to right. I'll use my fingers as limiters. And we see that the arrow down here is going to push this one off. The arrow up there is going to push that one off. So we have all real numbers for domain. For range, the up, down, the limiters are pushed off on each side, so it's all real numbers again. Please watch video number 1 if you're having trouble with domain and range. Over to our reflected linear function. Again, it goes forever left to right, forever up and down. So it's got all real numbers. It will go every direction. Now we come to the absolute value domain and range. Here we notice that the limits side to side get pushed out, so our domain is all real numbers, but notice how the range coming from the top and the bottom, the limiters, I'll use these pins, the bottom one can come clear up to 0. It's not going to get pushed off because there's no arrow tips coming at it. The top one gets pushed off because those arrow tips are lifting it off. But we can leave this limitation at 0, so our range is y is greater than or equal to 0. Now when we look at the reflection, what occurs is side to side, the limitations get pushed off, so the domain is still all real numbers, but look at what happens to your range. as your limiters come in, this top one can stay, the bottom one gets pushed off, but the top one can stay, so we say y is less than or equal to 0. So look at the effect of having this negative out in front. It reflected our graph, but also if we have a limitation in y, the number is not changed, but look at this. With a positive, it's greater than. With a negative, it's less than. Nice little pattern to be aware of when you're graphing. Okay. Next one is the quadratic. If you remember right, that was the U shape. Okay. The points 1, 1, 2 squared was 4, 3 squared was 9. And in the negatives, negative 1 times negative 1 is 1, negative 2 times negative 2 is 4, and negative 3 times negative 3 is 9. Well, we know from patterns in math that the way that we've reflected these others was to put a negative in front. So we may even just shortcut this process and say, well, for the reflection, because it's going to be down here in the pond, below the x-axis, for that reflection, I'm going to try just putting a negative in front of that. When we plug in negative 1 squared, negative 1 times negative 1 is positive 1, but then we bring in that negative. So we do get negative 1 squared is positive 1, but we add that negative, it becomes negative 1. So we have ended up taking those points and producing a negative answer with them when we square them. So the U comes down this way this time. Beautiful, isn't it? When we want that reflection, all we need to do is put that negative in front. Again, domain and range. Domain is limitless side to side because this U is going out. So that would occur in both of those. And in this one, we see the bottom limit can come up and rest at 0. So it would be y is greater than 0, greater or equal to 0. And looking back at the last pattern of what happened, I would hope that you're already saying with the negative out front that y is going to be less than or equal to 0. Nice to study those patterns in math. Really, really play with patterns, play with puzzles. When you're doing math, it'll increase the neurons firing just in that area of your brain so that you see them when you're working the math problems. Okay, x cubed, if we remember right, looked kind of like our quadratic on that side, but because cubes reveal the negative, on this side it flips down. We remember right from the beginning, there were no restrictions on range or domain. Ask me if that still seems confusing. Now on this one, the reflection, we want to see it reflect over this x-axis, so we're going to get that funky pond like we did in the linear, where it's down in here and up in there. Let's look at that. So we have y equals negative x cubed. We're just going to go with the pattern, assuming it's going to work. Here we had 1, 1. Now let's see if we plug in 1. We're hoping to get 1, negative 1. 1 times 1 is 1 times 1 is 1 times a negative is negative 1. Okay, so we see that is truly starting to go down. Let's check one of our negative numbers out. Let's go with negative 2. Negative 2 times negative 2 would be positive 4, times negative 2 is negative 8, times a negative would be positive 8. So it worked again. When we want a reflection, we simply put a negative in front of our parent function. Okay? Domain is unlimited, range is unlimited. Okay. Down at the bottom of this page, I would like you to give me an explanation of how you can get a reflection of any graph, and give me a couple examples. Thank you very much. We'll see you in video number 3.